Hello, everyone. Welcome back to CMPT 456 Information Retrieval and Web Search. Today, we'll talk about web crawling. Web crawling is to find and download web pages automatically from the web. Web crawler is the program that conducts web crawling. Its task is to collect the web pages on the web. As you can imagine, if you want to collect web pages from large web, there are a lot of challenges. First, the scale is huge. The web may contain tens of billions of web pages on the whole web. Not only the scale, but also the time is a challenge. There are many new pages emerging or changing at any given time. And we all know the web is like a big zoo. There is no central control of all the web pages. There is no an easy way to find out how many pages are in the web. Indeed, how to estimate the number of pages in the web is a huge challenge. To build a good crawler, there are some highly desirable features. First, there are some must-have features of crawlers. Robustness is one. Robustness means a crawler should not fall into spider traps that generate an infinite number of pages. In the hidden web, there could be many databases hidden behind the web. A crawler can issue queries to search a web database. Many web databases are so big, and also, given the combination of conditions in queries, a database can virtually return an infinite number of answers, each answer being one page. Therefore, if a web crawler cannot identify that it is querying a large database behind the web, then it may fall into spider traps. Another important must-have feature of web crawler is politeness. A crawler takes the bandwidth of a website. If a crawler keeps asking questions, asking for web pages from a website, the website may not serve its regular customers, its normal customers. Therefore, a crawler should be polite, meaning it should respect the upper limit of visit frequencies of websites so that it has a minimum effect on the bandwidth, available bandwidth of the corresponding website. In addition to must-have features of a crawler, there are also some should-have features of a crawler. For example, due to the huge scale of the web, a crawler should be distributed and should be scalable. That means it can handle a huge number of web pages, and also it should be distributed into multiple computers, multiple clusters. And also it should be efficient, and it should be quality, meaning it should get useful pages and do not consume their time too much on those not useful pages for web search. It should also keep the freshness, meaning it should capture the update in web pages. And it can be extended for different kinds of crawling tasks. This figure shows the basic structure of web crawling. The crawler starts with a set of seeds. There are a set of URLs given to it as parameters. Those seeds are added to a URL request queue. The crawler starts fetching pages from the web according to the request queue. Once a page is downloaded, it is passed to find the link tags that may contain other useful URLs to fetch further. If the crawler finds a new URL that it has not seen before, then the URL is added to the crawler's request queue or called frontier. The frontier may be a standard queue or may be ordered so that important pages move to the front of the list and should be crawled earlier. This process continues until the crawler either runs out of disk space to stored pages or runs out of useful links to add to the request queue. For a simple crawler, there are two major tasks. One is downloading the pages. Another is to find URLs from the current pages and add them into the search queue. A simple crawler maintains a frontier, which is a request queue of URLs that the crawler needs to download. They may be organized as a standard queue, or those more important pages can be moved to the front of the list so that they can be downloaded earlier, as we just said. Where to start? The starting point should be a set of seeds, which is a set of URLs given to the crawler as the input parameter. The simple crawler will put all those seed URLs into the frontier. Once a page is downloaded, it is passed to find for more link tags. If the crawler finds a URL that it has not met before, or the crawling version is outdated, then it adds the URL into the frontier again. This figure shows the basic architecture of a web crawler. Each crawling process includes several worker threads, and each worker thread performs repeated work cycles. At the beginning of each cycle, a worker obtains a URL from the frontier data structure, which gives out URLs according to their priority and politeness policies. The worker thread then invokes the HTTP fetcher, which first calls a DNS submodule to resolve the host component of the URL into the IP address of the corresponding web server, and then connects to the web server. It then checks for any robots exclusion rules, which typically are cached, and downloads the web page. If the download is successful, the web page may or may not be stored in a repository of acquired web pages. In either case, the page is passed to the link extractor, which parses the page's HTML content and extracts hyperlinks contained in the page. The corresponding URLs are then passed to a URL distributor, which assigns each URL to a crawling process. This assignment is typically made by hashing the URL's host component, its domain, or its IP address. Since most hyperlinks refer to pages on the same website, assignment to the local crawling process is the common case. Next, the URL passes through the custom URL filter. That is, for example, to exclude URLs belonging to backlinks sites or URLs with particular size extensions that are not of interest. And then the URL also passed into the duplicate URL eliminator, which maintains the set of all URLs discovered so far and passes on only never before seen URLs. Finally, the URL prioritizer selects a position for the URL in the frontier based on the factors such as estimated page importance or rate of change. Now, let's look at politeness. The reason we need to do politeness is that within a website, such as SFU website, there are many pages may contain many links to other pages in the same site. If we just simply collect all those web pages in a batch, we may have to download many pages simultaneously from one website. That may overwhelm the whole server. How to implement politeness? We use politeness policies. A reasonable web crawler should use only a very tiny portion of the bandwidth of a web server so that it does not affect the services provided to the web server to its regular customers very much. How to implement the politeness policies? Logically, a crawler can split the request queue into a single queue per web server. That is, we collect all the URLs belonging to the same web server into one queue. And a server queue is open only if it has not been accessed within a specific time of window. This is called the politeness window. This implementation guarantees that at a time at most one request to a web server is issued, and also the web server won't be buttered twice within the politeness window. However, this slowed and polite crawling process also may lead to some challenges. Let's consider a web crawler, say, can fetch 100 pages per second, not that fast. And the politeness policy says that it cannot fetch more than one page every 30 seconds from a server. Then how many URLs we need to keep the crawlers busy? A simple calculation shows that we need at least 3,000 different servers to make the crawler reach its peak throughput. So if we want to crawl many pages per second, and we need many URLs from many different servers. Let's look into a little bit detail about how to implement it. Now, suppose a web crawler search a website. Then indeed the website administrator can also work with the web crawler to provide some information to the web crawlers of what are the pages in the website that the crawler may find interesting and may crawl. This is through a text file called robots.txt. This is a web server administrator designed file. The purpose is to notify a crawler that what is allowed and what is not. As you can see of the crawler a robots text file is something like if you if you list the directories that the crawlers are not allowed to crawl, and also what would be the directory that the crawlers are allowed to crawl. One interesting thing about crawling is that crawling is not a one-shot effort, because many pages on the web update themselves from time to time. So in order to make the search engine updated, we have to crawl the page, update it again and again. If a page is updated, we need to visit it later and crawl its content. How can one crawler knows that a web page is updated? This can be helped with HTTP. In HTTP, the request head returns only header information about the page, but not the page itself. Using this way, the crawler can look at the head and check whether the page is updated before calling the whole page itself, because one whole page itself can be huge. A crawler can compare the date it received from the last GET request with the last modified value from a head request. As you can see here, the date in red circle here shows the last update time. Now it comes to one question. What quality guarantee should the crawler maintain in order to make the crawled web pages as updated as possible? Let's give a try. Probably the most straightforward thinking is to use some kind of freshness measure. Here, the freshness can be measured by the fraction of the crawl pages that are currently fresh. A page is fresh if the crawl has the most recent copy. Then, one page is fresh, then it takes a value of 1, and if it is not fresh, then it takes a value of 0. We can sum up the freshness of all the pages and try to maximize the freshness. Let's consider one situation. Suppose we have a website X. X changes its front page slightly every minute. How to optimize for the freshness in this case? One interesting observation here is that unless a crawler continuously posts X, it will almost always have a stale copy of the page. Therefore, it doesn't really matter. It keeps crawling the page as long as it cannot catch up with the updating speed, or it just gives up and stops crawling the page completely. If it will never be fresh, it cannot help the freshness value. That's the rationale. So, obviously, using the freshness measure cannot help to allocate the cross resources to pages that are changed frequently. Instead, it will encourage crawler to focus on those pages changed less frequently. In this sense, freshness may not be a good measure to use. In practice, many search engines use a slightly different but much more effective measure to measure the freshness of web pages. This is age. A page has age 0 until it is changed. Then its age grows until the page is crawled again. If we can consider the clear. For freshness, it is a binary variable. It is 0 until it is changed, and then it becomes 1, no matter how long the page is not crawled. It is always 1. And then when it is crawled again, the freshness is brought back to 0. So once a page has freshness 1, no matter how many updates it has, no matter how much time it stays uncrawled, the cost to the web crawler is the same. But for age, it's different. The age of a page is 0 until it is updated. Once it is updated, the age increases monotonically until it is crawled again. Therefore, the longer the page is updated but not crawled, the more cost it will take for the crawler. Therefore, the crawler has to look at those pages that have been updated for a while and then should try to catch up with those crawling tasks to bring down the overall age of the whole corpus they want to crawl. Consider a page with change frequency lambda, where a page is expected to change lambda times per day. The expected age of a page t days after it was last crawled can be calculated as follows. We take the probability that the page change at least at time t times the time t minus x, and dx, that's the age of the page after change. We sum that up from 0 to t. If we assume that the page updates follow the Poisson distribution, then we can have the age of lambda t calculated in this formula. If a crawler crawls each page once a week, and each page in the collection has a mean update time of once a week, then on average, the crawl will be 2.6 days old. The expected age of a page with mean change frequency lambda here is 1/7. Why should we optimize age instead of freshness? I hope you get the idea we just demonstrated using the example. In principle, the second derivative of the age function is always positive. Therefore, the age may not be monotonically increasing, but its increase rate is always increasing. The older a page gets, the more it will cause a crawler to not crawl it in terms of crawling staleness. Therefore, optimizing age never results in the problem that freshness has. Remember, we talked about the freshness. The drawback is that if a page is updated frequently, then because so many times its freshness is 1, as long as a crawler doesn't crawl the page in time, then its freshness is 1. But the freshness of 1 can stay there and does not increase. For age, it won't be the situation. The cost keeps increasing. Therefore, the crawler has to catch up with the changes. Remember, we talked about vertical search. Vertical search engines only search web pages about a specific topic, such as the movies. Vertical search is very useful because they're more accurate, they're more focused, and of course, it is also expected that search in vertical search engine is less expensive in computation because the database should be much smaller. How to collect the web pages related to a topic? How to crawl for vertical search? Of course, we can crawl a full copy of the web and discard all unrelated pages. Arguably, this is the most accurate approach, but it is very expensive because you first have to crawl all the web pages. In practice, people do another way. What people do is that they try to conduct focused crawling, or called topical crawling. It is a much less expensive approach. The idea is that we can try to use a topic classifier, which is a machine learning approach, to direct the web pages, the crawlers, to download only pages relevant. The web, indeed, has many different kinds of web pages. One part, called the deep web, is hard for a crawler to crawl. Here, deep web, or known as hidden web, refers to the set of sites that are difficult for a crawler to find. It is estimated the size of a deep web indeed could be hundreds of times larger than the traditional index web that a crawler can easily access. There are three major categories of sites in the deep web. The first is the private sites, intentionally private. For example, our course email archive is a private site, intentionally private. We set the login facility to keep the information confidential and exclusive only to the students and instructors and TAs of this course. So one has to use the login information to gain access to the archive. Also, we may create a web page to host the lecture videos of this course. As I do that in YouTube, indeed I list all the videos as unlisted, meaning please do not provide any search engine, any incoming links to those videos. Only the people with the link can access those videos. So those are the private sites intentionally private. The second category of deep web is form results. Essentially, it is a database hidden behind a web page. In order to access the information, one has to raise a query using the web interface, typically in a form. For example, consider the airline ticket queries. You have to input the information about the destination and the date in order to retrieve the airline ticket. Even you can fill in some queries through a form, a search engine crawler still may have a challenge to determine whether it already crawled enough data from the database behind, because there is no easy way to check whether a crawler enumerates all the possible queries given the database. And also, another challenge is that it is very hard to detect change behind a form. The third category of deep web is the script pages. A web server can use JavaScript, Flash, or another client-side language in the web pages. Those web pages even can be retrieved, but they still have the challenge is that the search engine have to run those scripts, for example, using a sandbox in order to observe the results. A crawler needs to execute the script. The execution itself takes time, which can slow down the crawling significantly. As you can see, deep web is very different from dynamic pages. Dynamic pages may be produced, may be generated dynamically, for example, by wikis, but they are easy to crawl. But private sites, they are static. Indeed, they may not be changed, but because without incoming links or the login information, it is very hard to be touched. Crawling is not a one-sided business. For example, let's look at this specific example. We have the priority attribute here, which tells a crawler the priority of this subdirectory within this website. And it can show to the crawler this is a more important directory. So a web crawler using this information can prioritize its crawling activities. In some kinds of search engines, we have to crawl not only web pages. We may need to crawl emails, word processing documents, presentations, or spreadsheets. They are a little bit different from web pages, and they may have new challenges to be crawled. First, the update speed is expected extremely fast. For example, a user may always want to see the current version of the documents. Therefore, we have to search for those updates frequently. Second, we may have to use operating system services to obtain update notification instead of using the robots.txt document. Third, a desktop crawler should not create another copy of the content because those documents already stored in the computer, and creating another copy could be too costly. And in the computer system, there may be a very rich file formats. Then we need to have different software to interpret and understand those formats. And last but not least, the data privacy concerns. Some users may want to protect their documents, and the protection should also cover search. That means a user should not be able to search another user's data. In crawler, they also use feed information to find updates. This is different from the usual way of the pooling. Pooling means the subscriber checks periodically for new documents, like checking your mailbox. For example, this is like a news feed or use the RSS. RSS is the really simple syndication RDF size summary. They can provide the rich size summary. Instead, user feeds can provide the push services. It can alert the subscribers to the new documents like telephone rings. So the subscriber can decide whether to access the updates given the alerts. Let's look at one example here. In this case, we have the one field TTL 60 here. This is time to live, meaning the contents should only be cached for 60 minutes and should be considered stale after 60 minutes. So in this XML document, it tells the crawler that every 60 minutes it should try to revisit this site and obtain the updated information. The web is huge. There are many pages on the web, and those pages are hosted by different web servers, and those servers are distributed all over the world. Crawling is a tedious work. You have to visit many web servers. Many of them may be distributed all over the world. Therefore, crawling typically cannot be done by only one computer. Indeed, crawling is usually done collaboratively by many computers. Not only by many computers in a computer center or in a data center. A global web search engine typically has to put the crawler closer to the websites it crawls. The major rationale behind this is that it tries to shorten the network connections to achieve higher throughput. Let's do a simple calculation. Suppose a crawler on average can copy 50 pages per second. Then it can transfer a page in 20 milliseconds. This is 1 second divided by 50. Then if it takes the crawler 80 milliseconds for a site to start sending the data, then in total, 5 seconds waiting time in transferring those 50 pages. If the latency time is 500 milliseconds in network, in total, the crawler needs 600 milliseconds times 50 pages equal to 30 seconds to transfer those 50 pages. That's a long time. Now, how can we crawl by multiple computers? The idea of crawling by multiple computers is to reduce the number of sites the crawler has to remember. It can remove the duplicates. A crawler needs to maintain the frontier in main memory, remember that. And also the larger the throughput, the less sites need to be kept. A crawler can use more computational resources to compute and can use more CPU time for parsing and network bandwidth for crawling. Distributed crawling is pretty much similar to crawling using one computer, except that now we have multiple computers, multiple nodes to conduct the crawling. The idea is to replicate the flow of a similar figure we saw before at each node, with one essential difference. Following the URL filter, we use a host splitter to dispatch each surviving URL to the crawler node responsible for the URL. Thus, the set of hosts being crawled is partitioned among those nodes. This modified workflow is shown in this figure. The output of the host splitter goes into the duplicate URL enumerator block of each other node in the distributed system. Please pay attention to this component called content scene. Indeed, there is some complication here. There are several factors we need to pay attention. First, unlike the URL frontier and the duplicate enumeration module, document fingerprints or shingles cannot be partitioned based on host name. Here, the document fingerprints and shingles are the features we can decide whether two documents are identical or not. There's nothing preventing the same or highly similar content from appearing on different web servers. Consequently, the set of fingerprint and shingle must be partitioned across the nodes based on some property of the fingerprint or those shingles. We'll talk about that later. The result of this locality mismatch is the most content scene test result in a remote procedure call. Second, there is very little locality in the stream of document fingerprint shingles. Therefore, caching popular fingerprints does not help here. Last, documents change over time, and so in the context of continuous crawling, we must be able to delete their outdated fingerprint or shingle from the content scene sets. To do so, it is necessary to save the fingerprint or shingle of the document in the URL frontier along with the URL itself. In the task to assign URLs to computers, let's consider if there are many computers, when a new URL is met, which has not been crawled in one local computer. How can we know whether it is crawled in other computers? One idea we can do is that we can use hashing, so that one crawler is in charge of one set of URLs. Therefore, we can assign the URLs from the same domain to the same computer. We only need to track the queue in one computer. This is implemented using computer hash value of a URL using only the host name. And indeed, we don't need to worry about whether there's any duplicate, because once we compute the hash value, it is a unique value and maps to the one computer. We also need to use the domain. A crawler crawls pages from the web, and then next it has to store the pages into the disk and the database. The first thing it needs to address is the conversion in order to store the crawled web pages into a database. The reason is that the text on the web is stored in many different formats. A search engine needs to convert all the text into a targeted text format like HTML or XML so that it can be stored and retrieved later in a consistent manner. For example, you can see here, this is an example of the text in the TREC Web Compound document format. In order to convert, we can use some character encoding. For example, we can use Unicode. Unicode is a single mapping from numbers to glyphs. We have different ways to implement Unicode. The general idea is that we can map bits into numbers in Unicode. For example, UTF-8 encodes as short as possible, while UTF-32 uses 4 bytes per glyph. Crawlers often use UTF-32 as the internal encoding, but UTF-8 to store text on disk in order to save the space. For example, here you can see for decimal numbers between 0 and 128, they are encoded into the 8 digits here, with the first digit as 0, and then 128 to 2047 with the 2 bytes. The first byte will start with 110, and the second byte will start with 10, and so on. In many cases, a search engine has to store documents in the database. This is essential because a search engine has to generate snippets, extract information, and manage updates. If a search engine does not store the data in the database, and instead it has to search crawl from the web every time a query is raised, then the user may have to wait for a long time for the answer, and also often the documents may not be available on the web all the time. The major search engines do not use the conventional relational databases to store documents because that may not be very efficient for large amount of data, text data. The volume of document data overwhelms the traditional databases. Instead, the search engines directly work with the operating systems to create its own data storage blocks and store the data there. The major operation here is to look up a document using a URL from the data stored in the search engine. How to look up quickly? we all know from our data structure course, hashing is a very efficient approach. Then the question is, should we store each web page using an individual file? The advantage is quite obvious. If we store everything using an individual file, then given a URL, we can immediately return the file corresponding to this URL. However, there are some challenges. Many web pages are very small in size. A page may be transferred in milliseconds. If we store those pages into individual files, then we may have a huge number of such small files. The hard disk time might be 10 milliseconds, as we know from our operating system course. Therefore, reading many small files needs a substantial overhead to open those files. How to handle this issue? How to solve it? One solution is that we can store many documents in a single file, pack them, so that transferring the file contents takes much more time than syncing to the beginning. This is more efficient because most of the time will be spent in reading the content instead of looking for the file. So a good size choice of such files could be in hundreds of megabytes. At Google, it uses one data structure called Big Table to organize data related to web documents. Essentially, Big Table is a working distributed database system used internally. It is a database contains only one table virtually, but the table is split into many small pieces called tablets, which are served by thousands of machines. For Big Table, there is no query language. There is no complex query. There are only low-level transactions which can be scaled up to very large database sizes. Essentially is that a big table is a very, very wide table. Each row is an URL, a web document. It contains many attributes such as the text, the authors, the title, and so on. And then, according to the storage of the data and also the similarity about the data, they build different blocks. Multiple attributes of multiple tables can be cluttered together into a block. So on this big table, there are only low-level transactions. Any change to a big table are recorded to a transaction log stored in a shared file system and will be used later for recovery in the case of crash. Big table can store data in immutable files which are unchangeable. And Big table can periodically merge files to reduce the total number of disk files. So in Big Table, the basic operation is adding new records, and it does not conduct the change or modification operations, so that it does not need to change the already stored data blocks. Essentially, the columns are divided into groups. Big Table can have a huge number of columns per row. Because we set almost all possible attributes as columns. But for one specific web page, they may not be all. They may not have values on all the columns. Indeed, a big table will be very sparse. All the rows have the same column groups. The rows are partitioned into tablets based on their row keys. If you want to look up a particular row, you just use the hashing to identify the tablet holding the row, and then you read from that tablet. In storing the web pages, one big challenge is that we have to detect the duplicates. Because we know one page may be crawled multiple times by different crawlers if they are not well synchronized. More importantly, is that the same page may appear in different web servers using different URLs. Indeed, there is a statistics showing that about 30% of the web pages in a large crawl are exact or near duplicates. They may due to different versions of a page. They may due to plagiarize and spam. They may due to using URL alias and mirror sites. Exact duplicate detection is somewhat easy. We can use checksums. Essentially, the checksum calculates a sum based on the characters on the page. For example, we can use the cyclic redundancy check, CRC. It considers the position of the bytes. So if the two documents have the exactly same checksum, then the two documents have a very good chance to be duplicate and thus can be detected. If the similarity between two documents is over a threshold, then we consider the two documents near duplicate. The near duplicate may caused by, for example, advertisement on the web pages. So the same page embedded by different advertisements, but the contents are still the same. Or there could be different affiliation, different host information, so that the contents are the same, but the two pages have a very small difference. So the search scenario becomes, given document D, we try to find all the near duplicates of D in an archive. Then this is a linear operation if there are n documents in total, because we only need to compare document D with everyone in the database. This is the search scenario. In addition to the search scenario, we may also have the discovery scenario. In such a case, we are given n documents. We try to find all the pairs of near duplicate documents in the database. In this case, a naive approach, we have to do a quadratic operation, because we have to compare every pair of documents. The central idea to conduct near duplicate detection is the following. Instead of comparing word by word, let's try to extract some features from each document. We use those features to distinguish the documents from the others. When two documents are compared, we compare the features. Hopefully, the feature comparison cost is much lower and still give us a pretty high accuracy in detecting whether the two documents are similar to each other. And then we can organize those features of documents in a way that can be retrieved efficiently. For example, we can do index such as sorted index list, or we can do hashing. One approach to produce such features is called fingerprint generation. In order to generate fingerprints, we can partition documents into words, and each word is passed. Those non-word content such as punctuation, HTML tags, and additional white spaces can be removed. Then we can group those words into contiguous n-grams for some small number of n. We cannot use all the n-grams because the number of n-grams is essentially the same as the number of words in the document. So we can choose some of the n-grams as the representation of the document. The selected n-grams are then hashed to improve the retrieval efficiency and further reduce the size of the representation. For example, we can choose the n-grams which have the following property, which are with the n mod p. That means we select all the n-grams whose value of modulo p is 0. Let's take a concrete example. Suppose we have the original text as tropical fish include fish found in tropical environments around the world, including both freshwater and saltwater species. We take a 3 grams. So the first 3 words becomes the first 3 grams, tropical fish include. And then we moved the sliding window to get the next 3 words. We have fish include fish here. And then we have include fish found here, and so on. So this is the whole set of all the 3 grams. We calculate some hash value for each 3 gram. For example, we can use the CRC code, or we can use the sum of the ASCII code of the characters in the 3 gram, and so on. Suppose the hash values are 938 for these 3 gram and 664 for these 3 gram. So you can see we have a series of hash values. Then suppose we select the hash values using 0 mode 4. So the first number 938, mode 4 is not 0, it's 2. So we do not take it. And the second one, 664, mode 4 is 0, so we take it. So we derived the hash value, the selected hash values using this formula and get the fingerprint of the 3 gram set. Then, to detect near duplicate using fingerprint, we can find all documents whose fingerprints match that of D. How to make the detection efficient? The idea here is that we can store the hash values in an inverted index. In such a way, we can treat each hash value as a virtual keyword. And then, for document D, we get its fingerprint, we search those inverted index and get the intersection so that we can identify the documents having the same fingerprints as D. Another approach is using shingling. In the shingling approach, we use every n-gram as a shingle, and let SD1 and SD2 be the sets of shingles in 2 documents, D1 and D2 respectively. Then, by the Jaccard similarity, which is calculated as this. However, computing the Jaccard similarity is quite time-consuming. Therefore, we think about whether we can approximate this Jaccard similarity. The idea here is that we can use a random permutation on those shingles. And then for each permutation, we use the first number in the shingle as the feature. And then if we have a uniform sample of those random permutations and pick the smallest item minimum value of the shingles in the permutation, then we may be able to approximate the Jacka similarity. Let's look at a concrete example. The third method to do this near duplicate detection is to use the SIM hash fingerprint. The idea here is that indeed the frequencies of words in a document may provide some useful features for the document comparison. The SIM hash fingerprint generation works as the following. We process the document into a set of features with associated weights. Here we use the frequencies as the weights. Then we generate a unique hash value with b bits for each word. In the b-dimensional vector, we update the components of the vector by adding the weight for a word to every component for which the corresponding bit in the word's hash value is 1, and subtracting the weight if the value is 0. After all the words are processed, we generate a b-bit fingerprint by setting the ith bit to 1 if the ith component of v is positive, and set it to 0 otherwise. Again, let's take the original text as tropical fish include fish found in tropical environments around the world, including both freshwater and saltwater species. We count the frequency of the words. For example, for the word tropical here, its frequency is 2 because there are 2 occurrences of the term tropical in the text. For term fish, its count is 2 because you can see there are 2 occurrences here. Then we produce the 8-bit hash values for all the words. Suppose the hash values are shown here, and we also associate with each term the frequency. Then we sum up those hash values bit by bit. For any value is 0 and this bit, we take the negative weight. For example, this is minus 2, and this 0 minus 1, and so the minus 3, and this is 0 minus 1, so minus 4 in total. Freshwater 0, so minus 1, minus 5, and then species 1, so we take the add 1 here, so minus 4, and fish 1, so take the weight, so becomes minus 2, and 0, because it's 0 here, we take out the weight, so minus 3, 1 here, so we add that weight is minus 2, 1 here, we add the weight again, minus 1, and then 1 again, now we add the weight, becomes 0. And we have the 2 ones here, so we add the weight here is 2. And this is 0, so we take out this weight minus 1, so we get 1 after all. Similarly, we can do the other bits. I will let you to verify the other bits by yourself. This is the vector v formed by summing the weights. And then we turn this vector into a binary vector, 8-bit fingerprint from this v. The idea here is that if the bit is positive, then I set it to 1. If the bit is negative, I set it to 0. So these will be the fingerprint formed from this V. And we use these to compare whether the two documents are similar or not. In crawling, another task is to handle noise. Because the main content of a page may take only a small display area of the page, and there could be many noise areas, such as the banners, the advertisements, the images, the general navigation links, services, copyrights, and other information. The challenge is how can a crawler remove those noise from the web pages automatically, because there are so many web pages on the web. It is impossible to use a human being to scan those web pages one by one and remove those noise areas. There are many approaches to do that. One approach is to use a heuristic. The idea is that, well, you can look at the HTML tag in the text of the main content of typical web pages, and then the heuristic says there are less HTML tags in the text of the main content than there are in those additional materials. So one thing you can do is that you use the accumulative distribution of the text. You count the number of tags along the token, words in the document. If the area is advertisement, if these are banners, and then the number of those HTML tags will increase. But in the main text area, like here, indeed, it will be relatively flat. So we identify this relative flat area as the main text area. Of course, this is a heuristic. The algorithm works as follows. We represent a web page as a sequence of bits. We have bn equals 1 if the nth token is a tag, and bn equals 0 otherwise. Then we can find the values pair of I and j to maximize the number of tags below I and above j, and the number of non-tag tokens between I and j. And these can be easily rewritten into the following maximization problem, is that we try to maximize the sum of all the bits below I and all the bits above j, but for the bits between I and j, we want them to be as small as possible. Or in other words, we want 1 minus this bn, the sum, to be large as possible. We may also use the document object model to representation to look at the different components of a web document. Typically, a browser creates a document object model representation when displaying a web page in HTML. We can navigate the DOM tree recursively to remove and modify those nodes in the tree by retaining only the main content. There are many extensions to do that. For example, we may use some visual features such as the position of the block, the size of the font used, the background color, and so on. And using the DOM tree, the multiple content blocks can be even identified and merged, or their relative importance can be identified. Today, we look at the crawling of the web. Indeed, there are a whole handful of interesting technical issues here. We talk about the crawling and basic crawler architecture. We talk about the politeness and frontier. And we discuss how to handle updates. And we mention deep web, which is difficult for crawlers to access. And also the sitemap, which will give crawlers some hints about the different parts of the web server, and then which directory could be interesting to crawl and which part should not be touched. We talk about document feeds. We talk about how to crawl in a distributed system. And also, we talk about how to store the crawled documents. First, we need to do the conversion so that the documents can be represented in a consistent format. And also, the documents can be stored in an internal database, and specific to Google, it uses Bigtable. And technically, we talk about how to detect near duplicate documents using fingerprints, shingling, and also SIM hash functions. And then last, we talk about how to remove noises. That's all for this lecture. Thank you. See you next time.